this one. It said like you needed to find the antiderivative.
Yeah.
And like I plugged it in now.
Oh, you have it here.
And I had it here plugged in -1.
So this was your antiderivative. Well, here's the thing. That needs to be nx.
Yeah. But I just plugged in the -1 because I was.
Oh, you plugged it. You were going to. Okay. I can give those back to you.
Thank you.
Okay. Can you take it back?
Thank you.
Yeah. All right. So on Thursday, we were talking about these logistic functions, kind of how they model population or some type of spread of a population or bacteria. I think we looked at a rumor example. And then we eventually, let me get this out here. We eventually were able to write a differential equation to model the rate at which this rumor was spreading. What we were trying to do, though, our goal in this section is to figure out how can we separate these variables to figure out the general solution. Okay, just like any other differential equation where you try to separate and integrate, we're going to try to do that here, but in order to do that, we had to first discuss partial fractions because we're going to have to use that technique here. So we're eventually going to get to this today where we can figure out that general solution. We're going to take a look at one more example, though, as partial fractions, just kind of as a warm-up. But what's a little different with this one is, do you notice how this fraction compared to the two other ones in your notes isn't the top degree more than the bottom degree? You see how we have an x to the 4th up top over an x squared? And that really wasn't the case on the ones we did on Thursday. We had an x to the 1st over an x squared, and then the same thing going on down here. Okay, so what we have here is an improper fraction. Like 11 over 7, okay, where the numerator is larger than the denominator. If that's the case, we're going to have to change the improper fraction into a proper one, kind of like a mixed number. You know how if you had 11 over 7, you could figure out 7 goes into 11 once, and then you have 4 left over, right? You can change an improper into a mixed. We're going to do that same thing here, just with some variables. So what we're going to actually do is go through the division of this to figure out what is that whole piece that we have, and then we can therefore figure out what's the remainder or the leftover. So what we're going to try to do is long division with some of these variables. Do you remember how to do that from pre-calculus? It's been a while. We're going to go through the division. So this 3x to the 4th plus 1 is your divisor. We have to be careful, though, that we use kind of zeros as placeholders because we're missing some terms. If we were to go through the progression, we're missing an x cubed term, an x squared term, and an x term. And we are dividing that by x squared minus 1, which is your divisor. Are we missing any terms in x squared minus 1? If you think about it, the progression of terms. We're missing an x, okay, so we're going to need that placeholder too. Do we need a refresher on long division? Maybe? Okay. It's all about looking at those first terms. So if the first term in the divisor is x squared and the first term in the dividend is 3x to the 4th, what do you have to multiply x squared by to get a 3x to the 4th? Can we think about that little mind game? What do you have to multiply this one by to get this one? Yeah. 3x squared. Okay, so that's the first term in your quotient. And with any long division of numbers or polynomials or whatever, the moment you put something in the quotient spot, you have to multiply that over by everything in the divisor. So 3x squared times x squared will give us the 3x to the 4th that we wanted. 3x squared times 0x would be a 0x to the third, and then 3x squared minus or times negative 1 would be a negative 3x squared. What do we do next in the long division process? Yeah? Subtract them. Okay, so we're always subtracting after each round. Notice how the first terms match, so if we subtract them, they're going to go away. Same thing with the second terms, they're going to go away. And next we have a 0 minus negative 3. So we're left with negative 3x squared. What usually comes next in long division? If you think about numbers. Don't you typically bring down the next term? Okay, you could bring down the next term. Maybe you want to bring down both. It really doesn't matter. Okay, because after all, we're still focusing on just the first terms. So now we're going to take a look at that x squared again from the divisor, and our new dividend first term is negative 3x squared. Yeah. This one? Yes. Sorry. Good catch. I saw those eyes, like there's something going on. You guys are looking at me and up at the board like something's off. Good catch. So let's repeat the process. What can you multiply x squared by to get a 3x squared? 3, good. All right, so we multiply that into the divisor. And we're going to subtract again. First terms match, so they go away. Second terms match, so they go away. 1 minus negative 3. We're left with 4. And that's our remainder. Okay. So what we can do is change this improper kind of polynomial fraction into a mixed polynomial fraction. The 3x squared plus 3 is your whole part. Okay, that's your quotient. And then your remainder is 4. And notice how in a mixed number you keep the denominator that you originally had. So we're going to keep that x squared minus 1. We're doing okay? All right. So now if you take a look at your integral, we could easily work backwards from the first two terms. And when we look at the third term for the fraction, it's no longer improper. The degree of the top is 0, because you technically have an x to the 0, and the degree of the denominator is 2. Okay, so it's no longer improper. Let's go ahead and work backwards. If we have a 3x squared, we started with an x cubed. If we have a 3, we started with a 3x. What do you guys want to try, though, for the last piece? Let's see, we talked about the reverse power rule and u sub. Those are the two big ones. And then we've been talking about partial fractions, if u substitution doesn't work. Do you want to try partial fractions? Okay, so let's go ahead and try that here. We're going to have to think about what did 4 over x squared minus 1 start as. So we have like a over some number or some quantity plus b over some quantity. How can we figure out those quantities? Yeah?
It's the difference of squares.
Different, yep.
You have x minus 1, x plus 1.
All right, so we're going to factor the denominator. Difference of squares, x minus 1, x plus 1. And if we were to actually add these together, we would have to take the x plus 1 denominator times top and bottom. So we would end up with an a times x plus 1. eventually up top. Same deal, if we took x minus 1 times the second fraction, we would end up with a b times x minus 1. And we want this numerator to match the numerator from the integral, which in this case is 4. So can we pick some strategic x values to help us figure out a and b? Good, Caitlin? 1. Okay, so if we plug in 1, 4 equals, let's see, we'd have a 2a, and then the b would go away. So it looks like the a value is 2. And what's another strategic x value? -1. So then in this case, the a would disappear, and we'd be left with a -2b. So we'd have -2 is our b value. Caitlin, do you remember your shortcut? No. No? It's okay. All right, so we technically, if we think about it, I'm going to write this over here. We have to integrate a over x minus 1, so 2 over x minus 1, and then b over x plus 1. Okay. If you were to integrate 2 over x minus 1, what did you start with? You can pull that 2 out as a coefficient, yeah?
2 natural log of x minus 1.
X minus 1, yep. And then for the second fraction, if we pull the -2 out as a coefficient, we would have the natural log of x plus 1. We don't know the bounds, so we would need that plus c. We haven't lost it from Thursday yet, right? That one was a little bit more involved because we had some long division to go through, but it still involved that partial fraction setup. Okay? So we're going to relate this back to the logistic growth that we started with. We wrote down this differential equation, and we're going to solve it. Okay, we're going to try to figure out y equals what is that general equation or solution curve. Okay, so first step is we have to separate those variables, get y's on one side, everything else on the other. So how might you want to separate those variables? What can we start to move? Yeah.
Multiply the dt over and divide ky minus 1 over.
Okay, so you want to divide both over? Or divide everything over? That's fine. I think if you want to do that, it should still work out. I think what I did is I just divided over the y and the L minus y, and I left the k on the right-hand side as a constant. But if you want to divide it over, that's okay too. So if we multiply over the dt, but divide over the y and the L minus y, it looks something like that. So now that the variables are separated, we're going to integrate or work backwards from both sides. Now, what you could do is, you see how this dy, I wrote it in the numerator? You don't have to put it there if you don't want to. You can do 1 over that fraction and then dy on the end. It means the same thing. Okay, it just depends on how you prefer to see it. Okay, so notice how on the left-hand side, we kind of have a fraction, so maybe partial fractions is a technique we can use, and it's already factored for us. You see those two different factors? We have the y and the L minus y. So we could probably try to do partial fractions for this one. We're going to have a over y plus b over L minus y. If we were to actually add those together, we'd have to multiply the opposite denominators. And that should equal the numerator from the integral, which would be 1. Now can we pick some strategic y values in this case to help us solve for a and b? Yeah. 0. Okay. So if I plug in 0, I would have a times L equal to 1. So the a value would be 1 over L. Is there another value for y we can pick? This time we want to cancel out a. Yeah. That's okay. L. Yep. L minus L would be 0. So it would cancel out that a. So we'd be left with b times L equal to 1, which means b is also 1 over L. We happen to get the same value. All right, so let's go ahead and figure out. We have 1 over L over y and 1 over L minus y. So if we were to work backwards from both of those, maybe using Caitlin's little shortcut. Remember, L is a number. Do you remember what that L represents in these logistic functions? It's your limit, it's your carrying capacity, like the highest population you could have. Okay, so we would have 1 over L times the natural log of y plus 1 over L times the natural log of L minus y. Are we okay with that? Just like the last one we did? Remember, L is a number. All right, so in terms of solving this differential, we figured out what the left-hand side is. Let's go ahead and take a look at the right side. Okay, so we're going to do that over here. The left side we already knew was 1 over L natural log of y plus 1 over L natural log of L minus y. What if we work backwards from the right-hand side? K is a number, it's a constant, and you're taking the antiderivative with respect to time, or t, not necessarily x in this case. Yeah, kt. And we don't know the bounds, so we would need that plus c. Are we okay so far? It's not over our heads yet, right? Not yet. Okay. It might get there because we don't have a single number going on in here. Okay. So we separated the variables. We found the antiderivatives. Okay. We do not have a point that we're going to plug in to figure out what c is. So our ending equation is still going to have a c in it. Our goal, though, is to figure out what the heck is y. Okay. Like we want y equals something. This is where it's going to get good. Okay. So let's think about this. We're going to dig deep, okay? If you are adding 2 logs together, what were you originally doing with those 2 logs? Do we remember some log properties? Long time ago. If you're, yeah, real long time, yeah. Actually, no, I messed up on something down here. Hold on. This should actually be subtraction. Let's go ahead and talk about that for a second. Okay, can we look at down here when we worked backwards? Okay, do you see how the variable is negative? We have L minus y. Yeah? Okay, if I took shouldn't I be able to take the derivative of this and I would get this back? Isn't that right? You could take the derivative to check your integral. If I took the derivative of this, you don't have to write this down, I just want you to look at it. You would keep the coefficient, then you'd multiply by 1 over the inside, which would be L minus y. Now what you could do is move the 1 over L to the top. Bless you. Oh wait, yeah. Coefficient times 1 over the inside times the derivative of the inside. If L is a number, the derivative of negative y is just negative 1. So we would have a negative 1 over L times L minus y if I move the 1 over L up top with the negative. But this does not match this exactly, because we were adding in this case, and notice how we're left with a negative. So a little tricky here, if your variable is negative in the denominator, we're going to have to cancel out that negative by putting in a negative when we find the antiderivative. Yeah?
How would we identify that without having to work through the whole derivative, or is there not a way to?
Without working through the whole derivative?
Yeah. You know how, like, we... Yeah, like, you know how we, like, did the...
So let's say it was something like that. Okay, I'll put in some numbers. This would be 3 natural log of x plus 2. You would then have the minus 2 natural log of negative x plus 4, right? That's how we would typically do it. But since that's negative, we would have to can't throw another negative out front, which would change it to a plus. Okay, since the variable is negative. We're kind of picking that up in that process. So that's going to change how we solve this for y. Okay, so I have to rephrase my question. If you are subtracting 2 logs together, what were you originally doing? Dividing. So we're going to keep that common coefficient out front, 1 over L, and we were originally dividing the insides of those logs. So y over L minus y. This is going to help us solve this for y, because notice how we went from having 2 logs down to 1. All right. Can we start maybe moving some of these terms or ideas over to the other side to help get the y by itself? For instance, how would you move over the 1 over L? Yeah. Multiply an L over. So if we multiply everything on the right-hand side by L, we'd have L, K, T. What about L times C? Just C. Those are both constants, right? L is a number. That's your carrying capacity. Can we move over a natural log? That would become a base of E. We have L, K, T as the power. Do we know where this constant C would go? Yeah.
It's multiplying.
Multiplied out front. Good. Are we okay with that? I know we talked about that last year. Are we okay with that C out front? Okay. What do you guys want to do next? We still have 2 y's. Somehow we got to get it down to 1. Bless you. Let's see. I don't like working with fractions, and I'm sure you guys feel the same way. So what if we took the denominator and multiplied it over? Do you think we could do that? So if we took L times this CE to the LKT, we'd have LCE to the LKT minus, and then we'd take the y over as well. We'll have YCE to the LKT. So that's nice because the fraction's gone. How can we change 2 y's into 1? What's your crazy idea?
Isn't CE to the LKT technically just a coefficient? So couldn't you add, like, this, for the y value?
Yeah?
Couldn't you add that to, like, the one coefficient or the other y somehow? I don't know.
You're going to add this over?
Yeah.
I like that. Okay, I like adding over that y term. Notice how we got the y's on one side, because that's what we're trying to change, right? We're trying to change 2 y's into 1, so let's group them together on one side. What do you want to do from there? Yeah. Let's take out a y. Notice how you go from 2 y's to 1. I don't expect you guys to remember this. I'm just trying to show you where something comes from that we're going to use on the next page, okay? So how do you want to get the y by itself? Just divide it over. All right. We did it, right? We got y equals something? Perfect. I'm going to change something, though. Isn't it true with a fraction, whatever you do to the top, you can do to the bottom, and it would still remain the same value in terms of multiplying? Right? If I multiplied the top by 2 and the bottom by 2, that's an accurate or logistic mathematical step. Okay? Take a look at this. Let's say I want to multiply, my pen's going dull. Let's say I want to multiply the top by 1 over CE to the LKT. And I do that to the bottom as well. That's mathematically possible, right? What you do to the top, you do to the bottom. Okay, so let's see what would happen if we simplify that. If I take LCE to the LKT times 1 over CE to the LKT, what am I going to be left with? Yeah, L, because this and this would cancel. So I'm left with L times 1, which is just L. Let's check out the bottom. Okay, if I take 1 and I multiply it by 1 over CE to the LKT, I'm just going to have 1 over CE to the LKT, which is a fraction. And I don't want a fraction in the bottom of a fraction. So can't I take this denominator and move it up and make the power negative? For instance, CE to the negative LKT. Okay, that's if I took 1 times this fraction and I move the denominator up, becomes a negative power. I then have to add whatever this times that 1 over CE to the LKT is. So what is CE to the LKT times 1 over CE to the LKT? If I took this times this fraction, do you see how these would cancel? You're just left with 1. Okay. This is what we're going to talk about on the next page. Okay. So I think we were okay with how we got kind of the black y equals equation, but notice how by multiplying by something a little crazy, okay, top and bottom, it's still appropriate though. We can change the way it looks. Okay. So on the back, if you take a look at the top, okay, if you have a differential equation that fits that logistic rate, okay, ky times L minus y, then your solution curve will always look like that in every single case. It doesn't matter what the k value is, it doesn't matter what the L value is. Okay, we'll eventually be able to figure those out, or maybe they'll even give them to us. But if this is your logistic growth differential, this is your logistic growth solution every single time. Do you see how we came up with that equation? Instead of me just giving it to you, we actually figured out, okay, where it came from. Okay, so it might be in your best interest to recognize these two, okay, the logistic growth differential and the logistic growth solution. Remember the L is your carrying capacity, kind of your limit, the highest you'll be able to use or go, and then the K is just some constant. Sometimes they'll tell it to you, sometimes you actually have to figure it out. We doing okay so far? Okay. Tomorrow we're going to take a look at this free response type question that involves using both the differential and the solution. Okay?